Good morning. I am Krishna Kumar from Krishna's classroom. We continue with our discussion on Riemann integration. Recall what is that we have done so far. We have investigated the problem of connecting Riemann integral with the computing the area function using Riemann integral to the what is called the antiderivative of the function. Now this has been successfully achieved and we have proved the fundamental theorem of calculus. With that it answers the relevant questions. Now we proceed in a different direction. What is it? We want to know which functions are Riemann integral. This is the point. Which functions are Riemann integral? We have partially looked at this question. We have seen that on the interval AB, that is, if f is a function from the interval AB to R, f bounded then 1 f continuous is Riemann. So we have a large class of functions which are Riemann. There is no doubt of it. Okay, so it works for a large class of functions. Secondly, we have shown that if f is monotone, then f is Riemann. In fact, monotone functions need not be continuous. And we already know that it may have discontinuities and it may have at most countable number of discontinuities. So, irrespective of what the nature of the discontinuities of monotone functions are, they are Riemann integral. And putting together the two things, namely that the discontinuities form at most a countable set. Therefore, there are functions with countable discontinuities which are Riemann integral. So we have now a large class of functions which includes all continuous functions, which includes all monotone functions, and even having countable discontinuities which are Riemann integral. So that is the current scenario. Now we have already seen certain examples where if the function has a finite number of discontinuities, one can prove that it is Riemann integrable by going back to the roots, that is using the basic definition of Riemann integration. But we also observe that we have seen that if it has f has far too many discontinuities, then it may not be Riemann integral. For example, look at the Dirichlet equation. That is the function which is one at all irrationals on the interval 0, 1 and 0 at all rationals. Now this function is not Riemann integral. Okay? It's a bounded function, perfectly well, but the problem is that it has discontinuities everywhere. So we have an example where if you have far too many discontinuities, it is not amenable to the technique that we have introduced to compute the integral. Now this is a problem. This is a problem that we look at. And now we would like to know precisely, if possible, which functions are Riemann integral. Some general result which gives some characterization of such functions if possible. Because you know that the difficulty comes from discontinuities. So we have to have a deeper analysis of the nature of the discontinuities. Okay. So we begin with the discussion on discontinuities. Quantitatively, look at discontinuities. So that is how we started. So we now, with this objective, we define what is called the oscillation of the function. Make it and then see what it means. Okay. Now, throughout this talk, we will be keeping f bounded on the interval a. It's a real valued function which is bounded on the interval a. Let a bounded function. Let J be a subinterval of we define omega f j by supremum of fx x belonging to j minus infimum of fx x belonging to and for x belonging to AB we define omega fx as limit goes to 0 of now omega fj is called the oscillation of f on the interval AB. Omega fx is called the oscillation at the point x. Now here we have to give say what lambda j is the length of now omega fj is called oscillation of f on j. Omega oscillation of so this is the definition that we use. Now let us examine what this is. First of all, whether our definition makes any sense at all. J is a subinterval of AB. Now you see that f is assumed to be a bounded function on AB and therefore it is bounded on J. Therefore, it is bounded above and bounded below. Therefore, the supremum of fx is on jx is infimum of f on j exists. For both these numbers are sensible and their difference is defined as omega fj. Therefore, omega fj exists. Okay, omega fj exists. And omega is certainly greater than or equal to 0. That is something that we observe. That's trivial to argue this. Now, therefore, we also have omega fx greater than or equal to 0 for every x belonging to so the oscillation is a non-negative number. Okay, right? It exists and it's non-negative, and that's important. Now we'll look at some examples to get a feeling for these things and then connect it up with what is called the continuity. Continuity and discontinuity. So we were after quantifying the discontinuities. So this tool seems to give you the right machinery to talk about the quantification. Okay. Let us look at some examples. First example, x belonging to two, and this is equal to 0 for x belonging to 1. So this function is defined on the interval 0 to 2. Now if you draw the graph of it, you can easily see that this is on the interval. This is 0 here, 0 is not included here, and then at 1, okay, the function is and then having a slope. This is the graph. Now what happens to this function? Now let us calculate omega f1 is equal to, you take any interval j, then the w f j equal to 0 if 1 does not belong to 0. This is equal to 3 if 1 belongs to. So this is equal to 2. Whereas omega f that's quite easy to verify. Okay, so it actually gives the measure of the jump that the function has at the point 1 or the discontinuity. Okay, and you see that at all other points this function is continuous, and we get omega accordingly, omega fx equal to 0 at those points. So look at another function. Upon x, now x is not equal to 0, and this is equal to 0, equal to 0. Now if you try to plot this function, now you see that the function is bounded between -1 and +1. And as x gets closer, let's take for x positive. So for x positive, you see that the function gets something. The oscillation becomes very rapid here. The oscillation becomes very rapid here. And so also on this side. Okay, let us take for x belonging to interval 1 to 3. Something like that. Okay. Something like that. So what happens is the function is, and at 0, you are defining the function to be 0. Therefore, let us compute the omega zero whenever x is not equal to 0. This is equal to, because what is the oscillation that you can have? You take any interval j containing 0 and then calculate omega xt. So this is going to be equal to 1. So this is the behavior of the function. Okay. The function comes from there and then oscillates. Okay. Right. Now what happens if the function is the Dirichlet function? Third example, take f to be the Dirichlet function. Now, what you see is that this function has a discontinuity everywhere, and you see that this is not something which you can easily plot at all. So, if you take any x, and if you take any interval j containing x, now you see that j contains both rational numbers and irrational numbers, and therefore the omega xj computes to be equal to 1. So you see that omega and therefore okay. Now we also make an observation that this function is Riemann integrable. This is also Riemann integrable, and this is not Riemann integrable. So the problem comes if there are far too many discontinuities. Okay, then the function fails to be Riemann integrable. So this is the problem. So we have to examine this more, deeply. Before that, we connect up these numbers with the continuity. So we have some results. I leave it to you to prove these results because these are very straightforward. Let f from AB to R bounded. Then the first result is f is continuous at C belonging to AB if and only if, very strong result, omega FC is equal to C. That's a nice characterization results in terms of the oscillation, or just a if you analyze this, you will see that it's just a rewording of continuity. That's why you look at the oscillation at a point, then you can easily decide whether it is continuous or not. 2. Let this is a bit more incisive analysis. Less than epsilon for every x belonging to AB then where x is delta positive such that mod fx minus fy is less than epsilon whenever mod now I don't want to prove these theorems or these results when they can be easily proved, make some arguments, quick arguments and do it. But we have seen some examples because omega fc equal to 0. Suppose omega fc is not equal to 0, what is the indication of that? See, you have on the interval there is some function here and then there is a discontinuity here. So at this point, suppose this is our AB, this is your C, then you see that there is a jump at C. That's the meaning of it. That's a discontinuity. And suppose the discontinuity is the measure of the jump is equal to some alpha. Okay? If it is alpha, suppose omega positive. Then what does it say? If it is alpha which is positive, then suppose you take epsilon to be alpha by 2, then for every delta positive, to see that mod x minus y less than delta implies greater than or equal to alpha by 2. That means you can find an epsilon with the property that for all delta, mod x minus y less than delta implies fx mod fx minus mod of fy is greater than or equal to alpha by 2. Okay, so WFC not equal to 0 implies f is not continuous at C. Okay, or in other words, if f is continuous at C, then WFC is equal to 0. That's one part of the analysis. The other part you have to, so WFC equal to 0, then f is continuous. Conversely, if f is continuous, prove that omega LFC is equal to 0. That is a direct analysis of this. We will have to use WFX equal to FC equal to 0, and then also take the J with the interval less than delta, so we will have to analyze this in definition. So that's pretty simple. Similarly, this is also possible for you to work out. If this is less than epsilon, then this is true. But here, one would have to use a different, a slightly more, sophistication in the argument, and that is, you can do this for every epsilon. You can do this for every x. You can do this. Therefore, you will have to find out the delta neighborhoods of x, and you see that the whole interval is packed inside the union of these intervals. Now use compactness of the interval AB. You can isolate a finite class of subsets. So corresponding to which you have delta 1, delta 2, etc. delta n. Then you can choose what is called the maximum of deltas for your argument. That is possible. So such an argument you will have to go through. So use compactness. Okay, so that gives a lot of information, connects up the discontinuities with the oscillation of f at the points. Okay, so what we have is now that we have already quantified. So oscillation, the concept of oscillation is a quantification of oscillation. So whenever the oscillation at a point is not equal to 0, the function is discontinuous there, and it's continuous if and only if omega at that point is 0. That's the result that we have. Therefore, now what we want to work on is the following. Okay. How much of oscillation you can have for a Riemann integrable function? This is the question. So we start with a Riemann integrable function and study the extent of oscillations that is possible. Okay. So that's the next part. So integrability and oscillations. This is what we want to look at. So how much of oscillations it can permit, or how many points where it can have oscillations, so that still the function is Riemann integrable. Okay. So we have already have some kind of knowledge or indications from the examples that we have looked at earlier, and now we can use that. Okay. So let us define the following. So we take f close without seeing. So we define D, the set of discontinuities, as the set of points x belonging to AB where f is not continuous. The set of all discontinuities of f. Now this is, of course, you know that this is essentially that's easy. So more precisely it is redundancy. Okay. Now you can see that this can be written as D can be written as the union 1 to infinity Dn, where Dn is defined as the set of all x belonging to AB such that omega f is greater than or equal to 1 by. For each n, you can define this for n equal to okay. So as n becomes larger, you see the oscillation becomes smaller. So all the discontinuities are now accounted for like this. So we write this as the union of. So this is something where you need to put your hand and give a proof for that. I mean, that should be fairly straightforward. So Dn is the set of points where the oscillation is the set of points where the oscillation of f is greater than or equal to 1 by. Now for epsilon positive, let us define d epsilon, set of all x Now what we do is we analyze the epsilon. So this is the set of points where the discontinuities is greater than epsilon, or the oscillation is greater than or equal to epsilon. So now we assume F is Riemann integral. Or in other words, what we are asking for is that how big d epsilon could be, okay, for such a Riemann integrable function. So let us analyze this. So we start with the definition. So this is the assumption, Riemann integral. So now we see F is Riemann integral. Implies given eta positive, there exists a partition P of AB say such that we have got UPF minus L in F is less than B. That's simply the definition of Riemann integral. Okay? Then we have a lot of results related to that. Now we define a set called S as the collection of all I n and xi minus 1 xi, this interval integral is. Which means you are simply picking up those intervals where you have discontinuity greater than or equal to epsilon. That's what it is. Okay? So you can subdivide the intervals xi minus 1 to two classes. One, the intervals where the discontinuities, the measure of the discontinuities of the oscillation of the function is less than epsilon, and the other set is the set of discontinuities on which it is greater than epsilon. And there may be, of course, that is always there, that wherever it is continuous, so that point does not come into our application. Therefore, what you can do is then you observe that d epsilon is contained in union I belonging to S of xi minus 1. This is quite pretty trivial to put this in the definition of this. And for every I belonging to I not in S, we have xi minus 1 xi intersection B epsilon is empty. Therefore, now let us make some estimates. Okay. So let us make some estimates. So we start from this. From here. Now let Mi denote the supremum of and small mi defined this is the usual definition of mi and small m. And then one can easily compute that eta is greater than UPF minus LPF. If you expand that and then drop certain sets, so you restrict only to the class of sets sigma I belonging to S. This is simple calculation. This inequality uses this. What is it? This inequality is the one that we use, and then the definition of S and all these details. All these details we use. Okay. Therefore, for each eta positive, we have intervals yes such that d epsilon is contained in union I belonging to S inside, and what more? You get sigma I belonging to S less than eta by. So what happens? You get an inequality, right? So this will be greater than or equal to. So this will be greater than or equal to epsilon into sigma I belonging to S. Okay, you use this. So what you get? Sigma I belonging to S, xi minus 1 is less than eta divided by this one. Okay, that is. So this is the consequence of Riemann integration. That is, if f is integrable, then d epsilon covered by closed intervals of total length greater than y. Something like what did we say? Less than beta by epsilon. That is, it can be made as small that's a result that we have. Okay, so we are looking at the set of points where the discontinuities, the oscillation at those points is greater than epsilon, greater than or equal to epsilon. And what we say is that those discontinuities can be, covered by a set of closed intervals whose total length is less than beta by epsilon. So you can make it as small as you want, because if the function is Riemann integrable, the choice of eta is what you can make. So you can make it as small as you want, and then what happens is the number of intervals will increase. But however, the total length of the interval can be made as small as you want. So we have the following theorem. We have shown that this is the result. Let a Riemann integral and d epsilon is the set of all x then for every beta positive there exists closed intervals I1, I2, finally Ik, rename them actually, contained in AB, such that d epsilon is contained in I1 union Ij, j running from 1 to k, and sigma j j equal to 1 to k So what it simply says is that all the discontinuities bigger than epsilon can be brought inside a finite number of intervals. A finite number of intervals. I1, I2, etc. I2. And also, the total length of such intervals can be made arbitrarily, made smaller than this. So this is the investigation that we have made on such functions. Now what we do is we go forward and then try to get the sort of information about the Riemann integrability of subsets. Okay, so let us do that. I will make some remark. So you see, you have now a way of controlling the set of discontinuities by packing them into intervals. Okay. For Riemann integrated functions, you can see that they can be actually packed into a finite number of intervals whose total length is as small as you want. So that is possible. Now we give the remark. Or it will be right RID. Theta positive, there exists open intervals. I1, I2, okay, such that d epsilon is contained in Ij and less than. So in fact what it says is that here we have obtained closed intervals in this discussion. We can as well replace it by open intervals. It's a small work to this. So whichever way you can have these intervals. It is not necessarily that the intervals have to be always closed. Okay. So what we prove next is a corollary which talks about Riemann integral functions. Okay, that means we see here we have what a sort of covering for d epsilon. Now what we want to do is we want to work on d. How do you get to d? D we have seen that d is essentially union B. So we shall make use of this to get a covering for B as small as we want. So that's our next task. Okay. So we will work this out. So I will just write down the theorem. Then we will do a proof. Okay. Here, let voltage no, it is enough to say Riemann integral. You don't have to say so much. Riemann integral. Then for every eta positive, there exists a sequence of closed intervals A1, A2, etc. Such that D set up for X for which F is not continuous is contained in union K equal to 1 to infinity J and sigma K equal to 1 to infinity this is the F is Riemann integral. For every eta positive, there exists a sequence of closed intervals J1, J2, etc. in AB such that this is not continuous at that set B of all points of discontinuity of F is contained in the union of these intervals and such that the total length of this interval is less than. So we do this. We use the previous example. So observe D is equal to union K equal to 1 to infinity. This is where Dn is, for which now apply the proposition that we have obtained for each n. then what happens? We get, using the above theorem, for d epsilon, we have for each n, you have, there exists closed intervals finitely many closed intervals I1 derivative, such that Dn contains union j equal to 1 to kn and sigma j equal to 1 to kn, the length of is less than as small as you want, beta divided by 24. So for each n we can work this out. So sir, this is just finitely many intervals. Now put all these intervals together. So it's a countable collection of finite sets. Therefore it is countable. Therefore we name Ijn for all j and n as then what one gets? We get that. Let me see that D is which is contained in union jk and sigma, the length of jk is equal to 1 to infinity j equal to 1 to kn lambda I j n, which is less than sigma, which one is beta by 2 to the power n. That's the result that we get. So D can be made, the set of discontinuities can be packed into a countable collection of intervals whose total length is less than beta for a Riemann integration function. Now this completes. Okay. So we got an idea of how big or how large the discontinuities of a Riemann integrable function will be. Okay. So we made a more incisive study of the discontinuities of the Riemann integrable function. Okay, so this is the final theorem that we have in this, that how what is the total, what is the nature of the discontinuities that we can have. Okay, what is it? The set of discontinuity can be packed into a countable, the union of a countable collection of closed intervals whose total length can be made arbitrarily small. Okay, so that's the whole idea. Now naturally the question is, if you have the discontinuities which can be packed into such a collection of sets, is it Riemann integral? This is the question that you would like to naturally ask. It looks things are fine here, because you see that if you have there are countable collection of discontinuities for the Riemann integral function, finite discontinuities for the monotonically increasing function, and for them you see that these kind of things appear there. So we are quite hopeful of that. So we made an abstract analysis of the discontinuities, the set of discontinuities of the Riemann integral functions. I think I will stop here today and maybe take up the continuation of this in the next lecture. So, thank you very much.